And we are doing so well mainly because of our excellent set of faculty, who have been performing so well, who have been, gone to some of the best universities around the world, including those in India, and got their PhDs from there, and they have come back and have been performing excellently. These faculty, along with their students and research scholar groups, have been doing exceedingly well. So we wanted to ensure that the world out there, including our own students, know about our faculty and their achievements and their contributions to the scientific community. As part of that as part of those efforts, we have started this seminar series, and I'm happy to start this series with the most accomplished senior professor in our department, Professor Sujit. He has got numerous awards. He's also a member of National Academy of Engineers and so on. So, I mean, his number of accomplishments are too large for me to enumerate in this group. So, without taking too much time, I request Professor Sujit to go ahead and start with this seminar. This will be the first of the series of seminars. We hope to continue this and then introduce all our faculty to the community at large, right? And then we'll continue this for next few years at least. Thank you, Professor Sujit.
Can you hear me? I was not having any voice last 3 days. I was sick, and I was very worried because I don't want to lose this opportunity to give this talk. But I have just about recovered my voice, and I'm happy to be here. Before I start, I want to thank the organizers, Sai Sandeep in particular. He told me quite some time back that he wanted me to talk. So I'm very delighted. Thank you very much. And I also want to thank my boss, Professor Murthy. He was also my first student when I came here as a fresh prof. Thank you for giving this chance to speak. And also we are able to do well, particularly because of the support from the administration. And I want to acknowledge the family of Professor D. Srinivasan, who used to be a prof here and who supports our chair professorship. And first and foremost, I should acknowledge my students. They are really having incredible, breathtaking talent, display absolute commitment, and really they show a lot of fighting spirit. I'm really privileged and proud to be working with such a fantastic group. And also, we need a lot of money to run the experiment, and crores and crores, and actually, thanks to all the companies and government agencies in India and abroad. Otherwise, we would not have been able to do any of this. It really costs a lot of money. And so without any further delay, let's get into a time machine and go back into 1960s when America was trying to get to the moon. We are also trying to go to the moon, and we actually landed here. I walked with many of you here together with goosebumps. India landing in South Pole and moon. And but they had more problems, and I want to talk about that problem. So this is the F1 engine, which is the workhorse engine. And the amount of power that this mission took when it was taking off, the power used by this rocket is more than the electricity consumption of all of a European country like England or Germany or something. That's the level of power you burn when a rocket takes off. And Saturn is a very big rocket. And best way to talk about it is volume. This is the F1 blowing up on the test stand.
Blowing up. Engineers finally identified the problem. Combustion instability, uneven burning.
If you visualize a candle burning in
Sunny Maria is project manager in June 1962, when NASA test fires its first F1.
When you try to fire it for the first time,
Blew apart. As F1 engines keep blowing up, engineers finally identified the problem. Combustion is uneven burning.
If you visualize a candle burning in a room, it flickers from side to side. Well, that's a form of instability. What happens there is
I'm quite sorry about all this acoustic problem. My subject is acoustic, but I guess I'm not doing very well. கொஞ்சம் வால்யூம் என்னோட வால்யூம் okay. So unfortunately I'm incapable of shouting today. I just regained my voice as I told you. So imagine there's a flame. Can you hear me now? Imagine there is a flame in a combustor. The flame makes sound, and the sound goes to the boundaries, gets reflected and comes back. And this is a good example of feedback. So here it is picking up some sound, getting amplified to the amplifier, coming back, and the microphone is further picking it up, sending it through the system, and giving out sound through this loudspeaker, comes back to the feedback circle. Imagine you are replacing the loudspeaker with a flame. So the flame is doing exactly like an amplifier system. Instead of amplifier, flame is amplifying. So the flame makes sound, goes to the boundaries, comes back, and in turn perturbs the flame more. So this feedback system leads to large amplitude sound, just as here you got this shrill sound. And this process is called, this phenomenon is called combustion stability and can drive very large amplitude oscillations. And in the test of this particular F1 rocket engine, now all these stuff is declassified, and the amplitudes were of the order of 100 atmosphere, or in excess of the mean pressure. Can you imagine? My sound, what I speak is 2 times 10 power, of the order of 10 power minus 5 Pascal, the volume with which I speak. Okay, maybe for some music can shout louder, and he's maybe 10 power minus 4, I am like 10 power minus 5. And this is 100 times 10 power plus 5, so 10 power 7 Pascal. You can imagine the level of sound, and it's so loud that the engine, it shakes the hell out of the engine, and engine blows up. And so this combustion instability, also known as thermoacoustic instability, is a problem that plagues all the aero engines and power plants and rockets, leading to catastrophic failure. And catastrophic as in it just simply blows up. It's not like it just does some, it's not like you caught cold or something. It's just the patient died, that kind of a thing. And it is an album of failures. There are lots of pictures. If you go to the internet, you will see of destruction. There's total carnage. And you can see these are, the heat transfer gets so high that the engine just melts. It simply melts, And there's a thermal protection system to keep your rocket cool and so on, but it just completely fails. And the thermoacoustic instability leads to catastrophic failures in aero engines and power plants also, the ones that make electricity with gas turbines. We can see because the vibrations are so loud, the thing cracks and blows up. But it may not be so spectacular like a rocket blowing up, but it's still, it's lots of money. And so you can see the damage. I have lots of pictures of damage. And this article from Wall Street Journal. I think I put this because B-Techs are often impressed with Wall Street Journal. I don't like the magazine, but maybe you like Wall Street, if not Journal. So you can see that things flew loose and nuts and bolts are flying out and hitting the turbine blades and causing a lot of damage. So what happened is, in the 80s, when I was a student, there was a lot of trouble. There were a lot of liberals making, crying that the world was going to end because of acid rain and so on. And of course, every time the liberals make a cause and try to raise hell, and then the conservatives find new ways to make money, because usually conservatives are rich men. So they actually came up with this new technology which supposedly could lower the emissions. I have to keep bringing water, my throat is not here. So emissions means oxides of nitrogen, NO, NO2, which will mix with water in the clouds and then supposedly fall out as nitric acid or something. So they said that oxygen and nitrogen don't combine. Right here there is a lot of oxygen and nitrogen. They don't combine. It doesn't combine. It combines when there is high temperature. So why there is a high temperature? There is a low temperature as a dilute mixture. That was the strategy, and it came up with the conservatives. And then they made this engine, and then this was supposed to be the solution. So it's called lean premix pre-vaporized. Okay, so lean means fuel lean or more air. And then when they took it to the field, things were flying apart. And then they had to have, they ended up, the machine will trip to protect it, because when this thing starts taking, or either blow, but before that, as it starts picking up, the electric machine will trip. And when it trips, you lose power. And of course, Americans are not used to saving. Here we save our fire, they don't save it every day or something. So the power is gone, the work is gone. And the other thing is, if I sold you a gas turbine engine, and your lawyers who write the contract will say that if the power goes, I will pay for the lost power and the penalties from the government and so on and so forth. Because every time power is lost, government imposes penalty, and you also lose your income. And all that thing has to be paid for by the guy who makes the gas turbine. So this is a very devastating problem for not only for rockets for space and military applications, but also for this domestic power generating engines. And there it is not that known that it's of the order of 1 billion or more, the amount of lost revenue and losses. But for space and defense, they will not let it fly unless it is completely cleared. So this program will come during the development, and then you will have to redo the thing. It will blow up in the test stand, but nobody will die because everybody is several kilometers away. And even then, I once spoke to people who did tests, and they think the rocket, the oscillations were more than 100 bars. It just melted off and blew up. And the people who heard the sound thought that they died. Since it was so, they were 7 kilometers away. So it is not exaggeration. It is really a wild thing. But you don't know how much money is lost in defense and space, etc., because that can be hidden under the guise of national security and top secret and all that. So you don't know how much mess you made. But the power plant, the stock, people who hold the stock, they will ask what happened. So you'll have to make it public. So imagine you were a suspect, okay, and then you wonder whether you have a heart attack. Oh God, I've been working too hard, I might be getting a heart attack. Or you ate something heavy, you had a sleep last night, and ate something heavy, too much gas, acid reflux. So can you hear me at the back? Okay. And then you don't know whether it's heart attack or heartburn, and so you think it's a heart attack, and you go to the hospital, call ambulance, 100 something, and get there. And then they tell you that you ate too much sambar yesterday or last night, and they give you Digene or Gelusil or something, but they send you home, and you look like a fool in front of your family, but they also give you a bill, and it's a lot, and then you will take out an insurance card, and then they will say, no, if you died, we will cover everything, including your cremation charges, but this is acid reflux, so, and you diagnosed wrong, but you have to pay everything, and this having sambar and getting into acid reflux, that is not covered by insurance. But if you die, you will surely pay next time. Now, on the other hand, you thought that you're actually getting heart attack, and you think that you just take some Digene on 10 ml or 5 ml, and that everything will be okay. You take, you don't wake up, and next day, your insurance company will be covering it. So identical symptoms and different problems. This is a hallmark of life. Lots of things in life, it is like that. Sometimes when I was young, I used to think, did that girl smile at me? Or maybe she was smiling at somebody standing behind me. So I can never figure out. So these kind of things you face every day. So imagine you are an engineer or you have your engine in the test stand. I cannot show the data from test stands because whenever I deal with data from government or industry, they make you sign this agreement saying that I cannot show it to anybody. So I really, I'll go to jail if I show that. So I have to take similar data in the lab and show it, but same thing, okay? So I'm just being honest, it's not industrial data, but it does very similar thing. So imagine if I'm on the test stand, either I am a human trying to look at the data and take action, or I may be a controller. Okay, somebody programmed me and I have to act. Okay, I'm looking. Now, I am young engineer, and I'm thinking this is going up. Then I think, okay, should I turn the engine off? But then I look, so this is the RMS value, root mean square. Then I look at the pressure amplitude. Okay, you take a Fourier transform. I guess you know Fourier transform. And look at the value. That is also okay. Is it going up? More austere, I don't know if it's going up or not. So the issue is like this. So it can continue to go like this. So because you assessing more airflow, you're changing some parameter. Naturally, if you increase the fan speed, you'll hear more sound, right? It could be that, or it could be a sudden blow up there. Now, if it was happening, and if I turned it off, then I do in the test, which each test costs crores, okay? And if I were in a private company, I will get fired. If I were in the government, I will get sidelined into some desk job. But if this happens, and the engine blows up actually, I will not be in any trouble because my boss will get fired before I get fired. Okay, so this is good. And one more thing, this kind of oscillation, they are low amplitude, aperiodic oscillations. It will not cause any damage within 3 years or 5 years, whatever period you paid your guarantee or warranty. But moment the warranty period over, the engine will break down. Why? Because this low amplitude aperiodic oscillations, they don't break the thing, but they cause fatigue and wear and tear, which will eventually break the engine. And when the engine breaks down, after the warranty, the company likes it because they have a lot of post-warranty business. And post-warranty repair is more expensive than actually buying a new engine. Okay, so these are the economical issues involved in it. So we want to know in this region that this is a green, everything is okay. And I want to know that in this region, see, if I got here, I know that I'm in trouble. And if I'm trying to measure my amplitude and say if it's trouble, I will know I'm in trouble only after I'm in trouble. So that is useless. I want to know whether I will get into trouble. That is the question that I'm studying. I hope it is clear. If not, please raise your hand and I will try to answer. Huh? So the objective is to prognose. Prognose it means that it is like you go to, you know, astrology. Astrologer, everybody knows astrology. If I go to astrologer and say tomorrow there is quiz of Professor Murthy, will I pass? So that is prognose, okay? Or maybe who is a touting prof, I don't know. So I want to prognose the onset of an impending instability. Impending instability means it has not happened, it will happen. The incipient instability means it has happened. So what companies do is to put a transducer, piezoelectric transducer in the engine and they will measure, and when the amplitude goes up, they will turn it off. Okay? But they have to turn it off because it already gone off. Okay? So this is the incipient. Incipient means already born. It's like I wrote Professor Murthy's test and I failed. Then I'm not predicting. But impending means, like the astrologer today, I can tell whether I'll flunk tomorrow or not. So that is the difference. Okay? Now, when I was a small kid, when I had cough and cold and sore throat and all that, I would go to a doctor. Doctor will check my pulse, put stethoscope here and all that. Now I don't go to hospital because if I go there, they'll put me in a scanning machine. Okay, all this fancy equipment and all that. But so can we listen? That's what the doctor does. Listen and so now if you go to a combustion research, they will have lots of fancy lasers and fancy high-speed cameras and all that. These things are useless in a real world. In the real engine, you can put one transducer, maybe at the most two transducers. Nothing more than that is possible in a real world. So, in a real world, can you listen to the sound and forewarn like an astrologer? I mean, I don't know if astrologer can predict correctly, but he's trying to predict. So whether your algorithm can listen and forecast a transition to instability. So the idea is to forecast. Boring people already they are walking. So the idea is to forecast combustion stability by listening to it. Listening is no fancy laser diagnostics and all that. Okay, I mean those things just don't work in. You cannot put laser diagnostics in an engine which has 20 bar or 40 bar pressure. Okay. So my wife always tells me that there's a big difference between hearing and listening, and she tells me that I always hear her, never listen to her. And I ask her what does it mean after many years. So she says that hearing means understanding the meaning of what he's saying. Listening means seeing the microstructure of the sound, how she says it. So she said there is much more information contained, and if you listen, you can understand a lot more than if you just hear understanding meaning. So she was saying that hearing was like my RMS pressure, and listening was by looking at the structure of the sound. Okay, and then we can get precursors. That, if I listen to if I listen to my voice, then I will know tomorrow whether I'm in trouble or not. The same thing, if you listen to the sound properly, you can predict if engine would get into trouble or not. So the signal will look like this. It will look very innocently flat, and I want to know if it's a real signal, and then it will suddenly go up. But can I know when I'm here whether it's going up or going to stay flat? So that is the question, and we want to know how close we are to the onset of instability. Because if we can go close, we want to go as close as possible, because that's where the high performance is. But you should not go beyond that. It's like an athlete. Athlete is trying to push her limit or his limit to the maximum capacity. But if you go beyond the maximum capacity, that is injury. So you don't want to get injured, but you have to be as close as possible to your limit. It's the same thing with the combustor. And so it is important to predict the proximity of thermoacoustic instability using data from stable operation. We have done for many engines. I can't show those results, unfortunately, but I can say one engine which you all know, the Chandrayaan lander, which you worked on, which you saw in action. So it's difficult to predict this critical transition because system shows hardly any change, and before it suddenly starts going up. And developing early warning is a very important thing for abrupt transitions because it can suddenly everything looks innocently sitting and suddenly it blows up. So I started with like a kid. I think those of you who took my class understand that I don't believe in classes, and my research also is the same way. So you have to think like a kid and try to figure out how it works. I'm sorry. So before you predict when something is unstable, that's blowing up, you should first be able to say what is stable. That's the thing. And people study, a lot of researchers study stable operation, they also study unstable operation. And then what is important is studying something in between. How does it go from stable to unstable? Something in between nobody looks. So what happens during the onset of an impending instability? Instability will not happen, but it's about to happen. I want to know what's happening. And I thought that if I could answer these questions like a 12th standard kid, 12th standard is the height of your intellectual prowess. And then once you join IIT, it exponentially decays. So if I try to work like a KV kid, I thought I'll have a shot at it, and it was correct. So this is our combustor, and you are all, by the way, welcome to come to our lab. We have a very, very nice lab. So this is our student. And I think this represents a gas turbine combustor. It is not a gas turbine combustor because we cannot, it needs a lot of space to get high pressure rigs and so on. We don't have that. So all we have is atmospheric pressure rig, but it has representative Reynolds number. You can do Reynolds number of 30,000 and 40,000 and so on, which are fully turbulent. You must have studied in pipe flow, what is the Reynolds number needed to get to turbulence? 2,000, yeah. So we have 40,000, something like that. So there is no problem. Okay. So we can actually, we also need a flame holding mechanism. Flame holding means if you take a candle and blow, you blow, right? So you have to have something which holds it, okay? And we can have it work as with solar, which I think the MTechs and third years and all will know, which will have a recirculating flow, which will constantly, so if you have a solar will centrifuge, and therefore there's a low pressure region, the flow will come back on. So if it comes back on, it will, the hot radicals will be there, so it will act like a spark plug, continually ignited. So we cannot put a spark plug and have a battery because it's very expensive, it becomes very heavy. Other possibilities of a block body, which you would see in afterburner. Afterburner flame is held with a V kind of thing. We can put V or any other block body. So we can switch between either of them, and that is combustion. And Vishnu is now a professor at IIT Hyderabad. Dilesh is working in applied mechanics. Great designers. So this is how it looks like in the lab. Like I said, you are welcome to come and see it. And this is the in action. We are acquiring data. So this is a control room, and this is the combustor running and so on, all computer control. Now we also have a crude version of the setup, like this, without fancy windows. You don't see the slide. Because, as I told you, I want to be like the old doctor in 1970s when I was a small kid. Or like, now only Ayurvedic doctors see, listen to the sound of the lungs and pulse. Modern medicine, they put you in the, what is that, equivalent of laser diagnostics. So I want, and even so, after strict instructions also, they made provision for 26 transducers. And I got very angry because I wanted one pressure transducer. So I made them close all these transducers. And then I put one transducer. I want to measure with just only one. Okay. I'm very adamant about it because only then you can use it in real world applications. The first question is, what exactly is stable operation? People called it combustion noise. That was the term which the engineers used. But engineers use a lot of terms, and engineers, difference between engineer and physicist is that physicist thinks he does not know anything. Engineer thinks he knows everything. So that is the whole difference. Actually, the reality, I don't know. So engineers call it combustion noise, but actually it is deterministic chaos. We have shown this guy was a BTech guy who worked with me. This was a PhD student. The beautiful combination. And yeah, in our group there is first year BTech to fifth year to MTech, MS, PhD, postdoc, also staff, everybody is there. So these guys showed that it is deterministic chaos. And if you don't know what chaos is fluctuating stuff, but it's very sensitive to initial conditions. So if you, for example, weather, they say butterfly effect, all you would have heard. So a small change in initial condition of a set of different equations can cause the system to go very widely different. That's why they say that if a butterfly flaps in Mexico or somewhere, weather here changes. So that is chaos. Small change in initial condition can lead to radically different trajectory of the system. So a chaotic tension is a self-similar structure. Self-similar means if you zoom in, you will see similar thing, and if you further zoom in, you will see similar thing. Like a Dracula movie or something. You keep zooming in and you will keep on seeing the same thing. You don't get to a fine resolution. And this so-called combustion noise signal, as I told you, it's combustion chaos actually. It appears to be self-similar. That means this picture, if I zoom in, I get this, which I zoom in, if I get this, but all have similar features. So to me, it appears to be self-similar. So let's discuss self-similarity a little bit. My promise to Sai Sandeep was that I will try to explain it in very simple terms. So let me not get into any complicated, fancy differential equations. We will write poetry. We'll copy some poetry. So clouds are not spheres. Mountains are not cones. Coastlines are not circles. Nor does lightning travel in a straight line. So this is a poem. I changed computer, so animation is getting messed up. But do you know who this guy is? Anybody? Not the PhD students, but BTech. This is Mandelbrot, who is very famous for fractals. Fractal is a rough thing. For example, we in class, we study, when you're in school, you study what is the perimeter of a square, what is the perimeter of a circle is 2 pi r, and so on and so forth. And then we'll study volume of a box, and prism, and cone, and all that. in reality, are there any of these things anywhere in the world except man-made things? Look at tree. Can you put some light? It looks so dark that I'm feeling sleepy. I'm not a night person. I'm already feeling sleepy. Ankit, can you find some lights and maybe put? It looks so dark. So, if you look at a tree is not a cylinder or sphere or something. That's good. Yeah. So a tree has a trunk which branches into branches. Each branch into branches, and they branch again and branch again so many times. Now, in case you are studying very hard and never looked at a tree, assignment number 1, tomorrow go and look at a tree. Same with clouds, same with everything in the world. Or our human body also. It is not, God didn't create it as triangles and rectangles and boxes. Blood vessels branch into blood vessels, they further branch. Same with these air passages, they branch, air passages in the lungs, they branch apparently 26 times or something. So these are still similar objects, and Mandelbrot was famous for studying these things. He passed away a few years back, didn't get Nobel Prize. I thought he should have been given. PT is a very similar signal. P of CT equal to P of T over C for H. Again, I think that the first year BTechs here and second year, they will be having, although you guys might have completely forgotten equations and all that, PhDs and all that, but they can understand. So P of CT looks like P of T. It's a scaled version. That's all it means. Okay. A function is a scaled function. Just the C for H is a scaling factor. Okay. And H is that scaling exponent. So what we are doing is zooming in the signal several times, and you will still see the same thing. That's what this scaling means. So nature displays self-similarity. In case you are studying very hard for JEE and never looked at a tree, here is a picture of a tree, and it branches, and assignment number 1 is to look at a tree tomorrow. Now, what about turbulent flow? Now, I can write poetry and I can write poetry, and but you know, aerospace engineers, we are in the business of either making money or killing. So why do we deal with fractures? And because our killing machines, they have turbulent flow. Now, are there any second years and third years here? Okay. They will teach you potential flow, inviscid flow, laminar flow. None of these things exist in the world. The only thing that exists in our world, at least in the engine, is turbulent flow. And they will not teach you that. I am also a propulsion professor, and I don't teach it, because I don't know how to deal with it. It is very hard, incredibly hard. Okay? Don't tell the prof, oh, you're recording it. Oh, my God. I'll be in trouble with my bosses. The turbulent flow, again, I'm sorry, the fonts for all, this was a beautiful font, but it got messed up. But there is a guy called Louis Fry Richardson, and he wrote a poem, and I'm on a poetic spree today. Big waves are little waves that feed on their velocity, and little waves have lesser waves, and so on to viscosity. He was a scientist, hardcore scientist, but he liked to write this parody. So you have, in turbulence, you must have, at least in the end, the last class, they will say there is something called turbulence when I'm teaching fluid mechanics. By the way, there is something called turbulence, happens at thyroid November, and there are some ADs. But by the way, I'll say no time, because class 42 hours only they are giving. I really need 88 hours, but they won't give. That will be my excuse not to teach turbulence. But reality, this is the only thing that is there. Okay, and so they are large words. If you don't forget classes, go to some of you swim, and you know, whatever you do, there will be some eddies. Or you can, if you went in a boat, you can look behind the eddies, or you can just stir the coffee, or put your hand in a bucket and all that. You can see these eddies. The large eddies break in the small eddies, it makes the further small eddies. So this is again a fractal kind of thing. Okay, that's what he wrote this poem on. So this is a picture of a turbulent jet, except that it's not taken in our lab. The volcanic flow. Okay, so this is a flume. This is a zoomed version of this. This is further zoomed. But all actually have similar structures. That is a key funda about self-similar objects or fractals. So turbulent flows are self-similar. Images of signals look the same statistically under increasing magnification, which is why we are interested in this business, because turbulent flow has this fractal nature. Okay? This was shown in the 80s. It was a big revolution actually. And fluid mechanics is there in our universe. astrophysical flows, large category of flows. In fact, many of the aerospace students whom I have taught, they went on to study astrophysics and high energy physics, blah, blah, blah. They say that our fluid mechanics here is better than what they teach in proper physics colleges, because physics departments don't teach much fluid mechanics. So I don't know if any of you took aerospace for that. And there's a galaxy, which is actually in fractal. If you zoom in, I don't have zoom pictures, but if you look carefully, you can see this kind of a swirling structure is replicated everywhere. So galaxies are also fractal. This is some kind of fractal broccoli, and you can see the ones generated with computer graphics and with the calculations and the real thing. It's hard to make out which is which, and in fact, this computer graphics has gotten so good even in the 80s that many of the mountains that you see, there's a lot of action happening on top of the mountain and all that. In this action movie, they are not mountains, they are multifactorial mountains actually, done with this calculation. Okay, it's a lot cheaper to do that, engage a PhD to do this rather than go and shoot on the top of a mountain. It's a lot cheaper. So what is fractal dimension? So fractal dimension is kind of fractional dimension. What is a fractal object? So we know that point has 0 dimension, line has 1 dimension, circle has 2 dimensions, the box has 3 dimensions, and so on. But I want to talk about half dimension, 1.5 dimensions, and so on. So what is, for example, if I take a line, this is 1 dimension. If I take a box, it is 2 dimensions. But what if I wrap a string so intensely, then it becomes 2 dimensions. Okay, so imagine, so this is a rhetorical question asked by this Professor Mandelbrot. How long is the coast of Britain? I guess he was a European, so he asked this question that way. He's originally from, I think, Poland. He lived in France, he was a Jew. I forget where he was, and we could ask any island. So if you take a picture from high up and you will use a ruler and the perimeter, how many times you place the ruler, right? That's how you measure. For example, when I was a small kid, you play cricket, 22 yards will be 1, 2, 3, 4, right? So similarly, or if you want to have 5 feet, 1, 2, 3, 4, 5. Never mind, my feet is smaller than a foot, but so if you zoom in, you will put more sticks, and if you further zoom in, you will see more and more wrinkles which you could not cover when you are zoomed down. So the perimeter depends on the size of the ruler. So the coastal perimeter versus the scale epsilon will have it will have an inverse power law. In the log plot, it will look like a straight line in reality. It's called power law, and power laws are ubiquitous in nature. So this slope is called fractal dimension. Okay. So now that is fractal dimension of a geometric object, and I told you different examples of geometric objects: clouds, trees, everything in the world. But time series is also fractal. For example, you can get your heart beat, and you can see your pulse, and you're seeing the pulse is having, it's a spiky signal. So this, it is called P, Q, R, S, T, something like that. So between R, there is a difference. Okay, when you put your hand on your pulse, or wherever you can feel your pulse, different people can feel it differently. Yeah. And what you feel is a kick, and the time interval between the kicks, that's very easy to measure. You can even do it automatically. And that time series of the RR interval, it is not periodic or something. As the doctors would say, pulse is irregular. They don't have no idea actually. It is actually chaotic and fractal and so on. In fact, the moment it loses the fractal behavior, you are gone. I will come to that in a second. So a fractal measures of dispersion such as standard deviation would not converge. Now what you do is you take the signal, split it into small segments, okay, and don't get worried. It is very simple. We know standard deviation, right? Everybody knows standard deviation. So find the average, then difference with the average, square all that, add and divide by n, take square root. Everybody knows this, right? Anyone who does not know standard deviation? Yes or no? That guy shook his head like this, like this. So, yeah, Lakshmi, you know what is standard deviation? Huh? Yes, okay, great, thank you. So we split the signal into small segments, find standard deviation, and of these things, and then you find the RMS of this, because the standard deviation normally we think that you have converged to some value, but it's not. And this quantity, RMS of standard deviation fluctuation, because signal is wildly oscillating. It is never, so, we studied Fourier series, sine wave, cosine wave and all that. Never exists in reality. It is this rough signal, okay. If at all you see a sine wave, you are in deep trouble, as I will come to in a second. So, in fact, if the heart is going periodic, you are going to die within 4 days. Seriously. So, if you take a log plot, power law would look like a straight line in a log plot, right? You can take log and then look up from y equal to x power a, you take log on both sides, then you will get a straight line. So, you see the log of RMS of standard deviation versus log of time scale, that has a scaling. Now, if you look at periodic signal is Euclidean. I mean, it has no scaling if you take long enough time series. White noise, that is a Brownian motion, you must have studied. It's a random process. So, that is an analytical result from physics, where it has an exponent half. Now, when you calculate it, it comes 0.502. Now, the sound from the combustor, when it is operating well, has a time series, has a slope in between these two. Okay? It is nice and fractal and chaotic and all that, which is why it is between these two values. Okay? Signals with a single scaling behavior are called monofractal, just one fractal dimension. Okay? Now, nature is more complex, and so initially they started using this monofractal description, that is one fractal thing, and all signals scale that way. But then people found that turbulence is multifractal. It means there are small amplitude fluctuations which scale in one way, medium amplitude fluctuations which scale in another way, large amplitude fluctuations scale in another way. So there are lots of sets of fractal dimensions. Okay, there is complexity. Because our picture of sine wave, we made it more complicated by saying self-similar. It's a set of several self-similar scalings. Okay, so it's really complexity, but we have the tools to deal with it. You don't have to approximate a sine wave or something. The tools are very well developed quite some time back. Except that we engineers don't know anything about it. So now we want to generalize it. So how do you zoom into small signals or large signals? Very simple. So if you put Q equal to 2, that is the RMS of standard deviation fluctuation. But if I put Q as a large number, that means and then take 1 over Q. What would mean is that when Q is a large number, Q is a positive number, let's say. So if I take a signal which is value of 10 and a power 10 by 2, I get 100. So I take power 10 by 3, I get 1000. So I can zoom in on the big signal because I'm selectively amplified. But whereas if Q is negative, I say 10 power minus 2, it will become 0.01. So if I have negative Q, I'm actually looking at small signals. If I have positive Q, I'm looking at large signals. So it is like a filter. Selectively, I'm picking large fluctuations or small fluctuations. I hope this is clear. If not, you can come to me afterwards and ask, or ask now itself. So this function, for whatever it's worth, is nothing fancy. It is RMS of standard deviation fluctuation, except I generalized it by powering it by Q and 1 over Q. That's all. So this is called structure function or fluctuation function. So we can plot for periodic signal. Whatever you do with a periodic signal, it will not show any scaling because it is a Euclidean object, not a fractal object. So it will be always showing some value. Now, white noise will always show the scaling exponent of half. Combustion noise, so the first exponent happens to be 2 minus fractal dimension. So the combustion noise, which is the sound which comes out of the combustor when it is working stably. Even when a combustor is working well, the one at home it is laminar, so it doesn't make sound. But one in the canteen there or in your mess, it will make a lot of sound because turbulence there. Okay, so that sound will follow this. There will be several different scaling exponents, which is good. Everything is peaceful. And if you look, you can actually plot HQ versus Q. For every Q, there will be HQ. But of course, mathematicians have a lot of fancy tricks too. They're always doing transformations. I will not go into the math, but I'll try to explain it in a physical way. So I told you that there are lots of sets of such scaling. So I have one scaling, another scaling, another scaling. So I try to get, so there are several scaling, and I'm looking at a function which represents what fraction of the scaling is there, what fraction of the scaling is there, what fraction of the scaling is there, something like that. And then I get a distribution. If lots of scaling are there, it will be having a big, broad distribution. If I have only one scaling, like a monofractal, or it will be just 1 point. If it is a periodic signal, it will be 1 point with exponent 0 because there will be no scaling. So, what happened to my pointer? So, this combustion noise, we have, this is a real signal, and it is multifractal. Okay. Now, professors are always accused of, and PhD students also, we are often accused of by the BTech of doing very useless things. Fancy, but useless. So the question that will be, BTech students ask, so what? So in Hindi you say, so kya? So actually there's a point actually. For white noise, you will get a dot at half because I told you it is analytical research. For periodic signal, I will get a scaling of 0. And for real stable operation of the combustor, be it swirl, like a primary combustor of a gas turbine engine, or like an afterburner kind of combustion. Everybody know what is afterburner. It's not, the gas turbine engines have a primary combustor, okay, which is what you usually use. And that's all the transport aircraft have. But for military engines, this, as I mentioned, that there's a lot of, we burn, effectively we burn at lower fuel than we can actually burn. So there is a lot of excess air. So imagine I'm going to bomb somebody. Imagine I'm going to come there to bomb you. I will come stealthily, without you tracking, hugging the ground, hugging the tree top. I will come there and bomb you. You don't know that I'm coming. You are caught off guard. Okay, like that strike in 2019, or any strike. But the moment I drop my ammunition, you know that I've come. And then everybody is, all these fighters are scrambling and trying to chase me. Okay? And what do I want to do? I want to go back to my base. If that is not possible, what do? I have to get back to a place where I have some friends there who enjoy air superiority so that enemy won't come near that, It's like, you have seen Tom and Jerry, and the mouse is Jerry, right? And Tom is chasing Jerry. But Jerry is not able to get to this place where, what is it called? Oh, yeah. But no way. But then he is really out of his life. What happens? Spike comes. Spike, Big dog. And then the cat cannot do anything. So, if you can't get your home, you have to get to a carrier group which will protect you from Gunda, where that guy won't come. You heard of quad and all that? Quad. No, you guys don't read newspapers. Quad. What are the countries in Quad? Any BTech? Quad. Yeah. So that is the alliance of navies basically. Right? So you understand why we need navy. So, okay, so afterburners, now you understand. So when you are trying to speak out, you are not trying to be fuel efficient or something. At that time, you want to run as fast as you can, and either get home or form a star that you can get to the big daddy who will protect you. Okay? Or he may not protect you, but the other guy worries about coming to a place where he doesn't have air superiority and the Gunda has air superiority. Okay? And the squad is 4 people trying to get more superiority, different places. Okay. So similarly, there will be other alliances also. Okay. So that is afterburner. So be it the afterburner combustor or primary combustor, you would have, if the engine is working well, you will have broad spectrum, lots of scaling. Okay. Now the problem is when it doesn't work well. Okay. So if it doesn't work well, you should get periodic signal. Okay, which is So this multifractality, which is a broad spectrum, it should collapse into this spectrum. Okay. So multifractality should disappear at the onset. So that is my answer to the BTEC to say that I'm doing useless thing. So it's a redefining the problem. Now the question is it going abruptly or smoothly? If it abruptly lost multifractality, then it's of no use, because anyway I know from RMS, if, for example, if I knew that if I write the exam and I flunk, then I don't need to ask anybody will I flunk or not, right? But I want to know before. So if the multifactor spectrum is smoothly collapsing, then I can know in advance. Yesterday itself I know that tomorrow I'm going to fail. Then you can decide, either you are going to fail, you can take the attitude, either I'm going to fail, so might as well have fun, or so I'm going to fail, I must study hard and not fail. But that is your choice. What action you do is engineer's choice. So let's go back to 12th standard Kendriya Vidyalaya kit. We go from stable operation or unstable operation. Stable operation is combustion noise, which actually is combustion chaos, which is multifractal and all that. And this full-blown instability, that is unstable operation. And full-blown instability is nothing but periodic operation, sine wave. And sine wave is a very dangerous thing if you get it. So transition from stable to unstable operation is a transition from chaos to order. Okay. So transition from health to ill health is a transition from chaos to order. Chaos is healthy. A healthy heart is a fractal heart, is a chaotic heart. Order heart is deep order. So how do you go from chaos to order? If you go to NAC building, I went there to take this picture. Well, so how do we go from chaos to order? We know how order emerges from chaos can come from order. Let me inside and I will make it chaotic, but the reverse is what you are looking at. Okay? So I will try to play this sound, but that dude disappeared. So if I play, you will not most likely hear anything. But he said that I should turn it off if I. Now, full-blown instability. Now, it is limited by now this 100 bars, don't be able to pass. We don't get 100 bars, but sometimes we get 20,000 bars. How building like this. And in between, so this is So this is feedback, very good demonstration. Can you hear? Yes or no? Yes, okay. So this is how the signal look like, plotting. I like to listen to the sound and feel the sound. That is how we discovered this. This was actually discovered by Vineet, but how we discovered is a very interesting story. So we made this combustor, it was a long fight. And we made this combustor, and there is Professor Sujit, who is expert in combustion technology, and I told my students that I will demonstrate how to do this and all that. And I am playing with all these things, and I am making mistakes, and then we are having to shut down the combustor. This happened 3 times, and my students got very angry. They said, now we will do, because it's very difficult, it's very hot, and at that time we didn't have these automatic controllers and all that. So they told me, go and stand it. So I went and stood near the door. They said, you can stand there, don't touch anything. So I went and stood there. Then I saw the experiment, and then I was watching them, because they told you cannot touch anything. because already 3 times I messed up and it's taking 7 hours. So, and I'm looking, and this guy Vinit is now a professor at Bombay, IIT, and he is he is controlling the airflow rate with computer. And I was seeing his shoulders, I was standing behind him, but I'm at the door. And he's getting very stressed, and his shoulders are getting tense and tense and tense. At some point, I thought he will burst off. And then instability came, and he was relaxed. So I think we are not worried about disaster. We are cool with disaster, but anticipation of disaster is what makes us tense. And then next one, I saw another guy. There was this Girish, Professor Girish. He's a professor in Cochin, Kusat. And he was a very handsome man, looked like a film star. He reminded me of Mallu star, Mammootty. And a very smooth face and all that. But his nice and smooth face started getting wrinkled. And it suddenly looked like he was aging 20 years. And it looked like his face had so much lines that out of the stress. And then I thought it would burst of this. And then instability came, and he was back to being very handsome. So I understood that people have inherently some way of knowing something happened. By the way, you can hear, no? I think I cannot hear what I'm saying. So when tsunami came, no animal was dead. They could go away peacefully. So I think we have in it some instinct that if you pay attention, you can do this. So after some time, how long can you see somebody's back or somebody's face? So I went to my room. And they were running again, and I was trying to listen to a sound, and I could make out that I could progressively sense from my ears that something was going to happen, and it happened. So I understood there was some field that our human body and the system had for this. Now the issue is, can you put this into some kind of calculation? And we saw this in thermoacoustics, aeroacoustics, aeroelastic. Aeroacoustics is, I will show you an aeroacoustic device I have in my bag. This is flute, which is an aeroacoustic device. So now I will venture into scaring you. So if I did not know how to play flute, which is quite likely, I will hear. That's what the sound I hear. So you can see any of your neighbors learn to play flute, this is the first sound you will hear. And eventually, this is the tone. But in between is the most annoying phase where they don't get this angle and pressure correct. So I am blowing steadily, but this is coming in burst. So you can try it with this fruit, or maybe you should not, because I am having a lot of bacteria and virus in my throat. So this happens in every oscillatory instability. It can be in wing flutter. You must know wings can flutter, or in this kind of thing, or combustion instability. And it has universal characteristics. Yeah. So we go from stable operation, which is in combustor case, it's combustion noise, via intermittency to full-blown instability, which is periodic oscillation. Not just for thermoacoustics, but any aeromechanical instability such as aeroacoustic, aeroelastic, flow-induced vibration, and surge. Flow over buildings and all that. Buildings can shake when there is very designed for that. So I don't want to put a PhD student, although professors often treat PhD students as not that don't pay very well, but it's not a good idea to put a student and look at how much stress they feel and decide whether instability is coming or not. So we have to automate, we have to develop tools and measures to quantify this transition from chaos to periodic oscillations via intermittency. So we see this is pressure amplitude, this is low value, this is where instability. And here is another, this is for swirl, which is the primary combustor, this is for the afterburner kind of thing. Pressure is staying low and then it went up. But you can see that this slope, which is called Hurst exponent, which is 2 minus fractal dimension, well before the amplitude changes, this thing is falling rapidly. So this Hurst exponent smoothly approaches zero as we approach an impending thermoacoustic instability. And as we approach instability, this broad spectrum collapses into a narrow spectrum. So there will be a loss of multifractality. So this is a nice breakthrough by my students. And so now we know whether you are going this way or this way. We know that this is a problem because we know from the Hurst exponent. So we know well in advance. Okay. And the amplitude has an inverse square law scaling with Hurst exponent, which will help predicting the amplitude. Because if you have a signal when it is stable, you know that if and when the system went into instability, from the scaling we can calculate the amplitude. This was again one of a PhD students. And so the traditional measures will look whether the amplitude is going up or not, but these early warning measures can come much early, and there's a lot of time you have to take control action if you have early warning. Okay, so we have a number of patents on this topic, and this is tested in industry also. Also in rockets, I told you we can use it to find stability margin. So complexity, a good system is complex with lots of scaling, and the collapsing of complexity goes away, and that is trouble, instability. So onset of thermoacoustic instability corresponds to a loss of complexity. Multifractal spectrum is actually showing complexity. So engineers, as soon as they get the signal, they will immediately filter out, call the signal and that noise and throw away the noise. But these are actually chaotic fluctuations. They are coming from turbulence. They are real, and so that's where all the information is. Don't trash the irregular fluctuations. So the signal plus noise paradigm, that's what we use engineers. But that is good for describing a instability that already happened, but not good for looking for something which is going to happen. So the irregular fluctuation holds the key. Now I started with my slide on heart, some guy having chest pain and all that. So is there anything more similarity between heartbeats and how combustion works? So transition from combustion noise to order corresponds to a loss of multifractality. Now congestive heart failure also corresponds to loss of multifractality. So the very striking resemblance. Nature prefers chaos and disorder and not really order. And because anytime you are going towards order, you are going to have a problem. So this is quite some time back, maybe 15 years back, Toyota had an ad. So, you don't think that you will get heart attack. No one who got heart attack thought they will get a heart attack. They would think that other people will get heart attack. So you won't go to, after getting heart attack, you end up in the hospital. Ideally, you should go and check every day, will I get the heart attack, will I get the heart attack? But nobody is going to go, nobody has time. So Japanese are very clever. So they put these electrodes in the car steering, because in Japan, they are very stressed people. So there were a lot of accidents because people get heart attack while driving, and then you die, and you take many other people along with you to heaven. So instead, if you are, when you hold the steering, if the electrodes can catch your pulse, and then if it can, it will do this calculation, calculate the Hurst exponent and all that. And if you are going to have a heart attack, and you can predict up to 4 days in advance, then you don't let you crank the engine, but instead ambulance come. Now we don't need such fancy things. Your iWatch also has this algorithm. Okay, wearable devices now. Okay. So a turbulent reacting flow is really a complex system, and we want it to be complex, and loss of complexity is what is trouble. Same as in health. So we are viewing thermoacoustic instability turbulent combustion as order emerging from chaos in this complex system. Now complex system theory, it was there for a long time, from the 80s onwards, but it was considered a fringe subject in engineering and physics. But now, not anymore. 2021, we got Nobel Prize. These three guys, Manabe, Hasselmann, and Parisi got Nobel Prize, and now it's a cool subject. So now I want to talk about mitigation. Okay, if you have early warning, you can avoid it, but what if you want to go through it? So if you know that you're going to flunk the test, if there is a possibility, you can take a makeup. Now you say that you're stressed, you go and tell the administration that I'm stressed, I want to take exam later. That is, take evasive action. But how do you, I want to write tomorrow, I know I will fail, then how to pass, how to mitigate the problem. So passive control is usually done by trial and error, which is very expensive. That's how they actually stop instability. They make this, they make lots and lots of changes. In this F1 engine, which I spoke about in the beginning, by the way, on YouTube there are lots of videos of F1 engine blowing up. They actually did 2,000 tests, I think, in that time, and it cost several $1 billion at that time's dollars. And now it must be even more expensive. So this thermoacoustic system have an Achilles heel. So Greek mythology 101 now, 1010 now, we have 4 numbers. So Achilles was a Greek warrior And Troy is a very nice film. There are different versions of it with different names. Are you an Achilles fan? You're trying to get up. So Achilles was vulnerable in this critical region because his mother, Thetis, she dipped him in river Styx and she was holding him in his heels. So that part she should have put some extra water after that. She didn't. It was not wet, so heel is vulnerable. Okay. So can we disturb the Achilles heel of a thermoacoustic system? If there is a Achilles heel and disturb it. So that is the idea. And these are the dudes who did this work. So a best way to study a complex system is constructing what is called complex network. So you have different components interacting with each other and you connect them. Okay. And the nodes represent the components and the connections represent the interaction. Okay. So this is, for example, an airline network of Emirates, I think. So you have airports are the nodes and the flights are the connections. This is a friends network. You all have lots of friends. But there will be some introverts who may have just one friend or two friends, but someone may be having a lot of friends. So you can construct the network. There is how Facebook works. Right? In fluid flow, there is no connection. There is no line connecting two elements in the flow. But you can find the correlations and find the connections. The connections are hidden, but you can actually find them. So we can construct a correlation network. There are other methods also to construct networks. And so we can measure the velocity either with experiments or with calculations. And we can construct networks with this data. And we can look for points which have a lot of connections. Example would be, imagine Yogan Raj is a cool dude. Everyone is friends with him. So he's like a hub. If I don't know you, I don't know you, I don't know you, but I know Yogan Raj. But so you not only know Yogan Raj, but know me, although we are not connected. He is connected to him. So if I know you, I can connect you. So if there is a hub, then everything is connected. So there are some hubs. If I can disturb that, that will destroy everything. And it will make the system stable. Okay, that is the idea. So what we did is to send a Shottu jet, Kutti jet into this region and disturb the region. And actually it stopped the instability. The amplitudes came very low. And not only that, this is the original picture. Now it just removed that critical region also. So this is a way to mitigate or suppress thermoacoustic instability. So combustion dynamics is complex, and a lot of profs say that it is a beast. A lot of engineers also say it's a very difficult problem. It's a beast and so on. But what do we do with the beast? We actually shy away from the complexity. What we first do, we will average the equations of the fluctuations and filter them out and throw them out. And then this is what we do. And then we linearize. And then we'll say, we'll have although we started with a line, which is our thermoacoustic system, we ended up with a linearized form. So that's what the way we engineers analyze it. But let combustion dynamics be complex. We like complex systems, it's very strong actually. And this is a good, complicated, complex system, what we have. So you should really test it with that. So it's the very complexity gives us engineering solutions. So I would say complexity is our friend. Embrace complexity. Thank you. I will be, if you are really fed up and bored, you can leave. If not, I will be here happy to answer your questions, also demonstrate. We can demonstrate. And in the meantime, we set up. I'm sorry, I have very nice fonts, but it's not my computer. Apple fonts don't work on PC. We'll demonstrate you a little thermoacoustic system. So my PhD student drew it, very high funda guy. But the more high funda somebody is, more simple they make it. You can do it. I can put, if the light is on. Okay. So there is a, where is which one are you using? This one. So this is a tube. There's nothing in it except there is a, okay, there is a wire mesh. Can you see? Nothing else, no? There's no loudspeaker. Do you see if there's a loudspeaker? No. can hear. So he's just making the mesh hot and just leaving it. It might take us to here. Okay, that's fine. I exhausted the last. But if such a small tube can make so much sound, you can imagine what is the power consumption in a liquid rocket motor? I taught you proportion. 30 gigawatts per meter cube. So a small fraction getting into sound can shake the hell out of it. So you can do this at home. And we can also, if you come visit our lab, we'll show you the compressor. So I'll be very happy to answer your questions on any of these things or anything else for that matter. Does anybody have any questions? The online audience can also ask questions on you. Like my class.